In this lesson, we are going to learn about trig identities. An identity is a mathematical statement that is always true. Here is a very important identity that you need to know. We call it the quotient identity, and it is true for all values of theta. Let's choose any value for theta, say 59 degrees. If we use a calculator to work out tan 59 degrees, we will get the following answer. If we use the calculator to calculate the value of sine 59 degrees over cos 59 degrees, we get exactly the same answer. This will always be true, no matter what value you choose for theta. Please note, if we square both sides of this identity, it will still be true for all values of theta. Also note, cos theta may not be equal to 0 in this identity. Do you know why? Because then you will be dividing by 0, and you may never divide by 0 in mathematics. The cos graph clearly shows that cos theta is equal to 0 at 90 degrees, and then every 180 degrees after that. This will also be the case when you go to the left of the y-axis. If we now add the tan graph, we can see that it is undefined at the same places where cos theta is equal to 0. In other words, this identity is undefined where tan theta is undefined, or where cos theta is equal to 0. The second identity you need to know is the square identity. You need to learn these two identities off by heart because neither of them are given on the formula sheet. Let's check whether the second identity also works for any angle. Here I choose the angle 43 degrees. We need to enter the following calculator keys to calculate this. Take careful note of the brackets I used to make sure that the whole of sine 43 degrees and the whole of cos 43 degrees is squared. No matter what angle you choose to use, the answer will always be 1. This is what makes it an identity. Please note, if we subtract cos squared theta on both sides, we can also write this identity as sine squared theta equals 1 minus cos squared theta. Or we can subtract sine squared theta on both sides to get cos squared theta equals 1 minus sine squared theta. By rewriting the identity in this way, we get the difference of two squares. In other words, sine squared theta also equals 1 minus cos theta times 1 plus cos theta. In the same way, cos squared theta also equals 1 minus sine theta times 1 plus sine theta. Writing it in this way can sometimes be very useful. These are the two identities you need to get to know like the back of your hand if you want to have success with trigonometry. Here we are asked to simplify an expression. There are different ways of doing this, but let me give you a good tip. Whenever you are given tan in the expression, change it to sine and cos using the highlighted identity. In this case, we need to square it, because we are given tan squared theta in the expression. Next, we multiply out the brackets. And because it is always a good idea to have fractions with fractions, let's rewrite cos squared theta as cos squared theta over 1 in the second term. Next, we can cancel as follows. This gives us cos squared theta plus sine squared theta in the next step. I hope you recognize what we have here. Yes, this is the square identity, which means that the final answer is 1. Please pause the lesson and make sure you agree with all the working. Let's do another example together. What do you suggest we do first here? We cannot do much at the top, but we do have tan x at the bottom. So let's use our quotient identity to change it to sine x over cos x. Next, we need to get one term in the denominator. The lowest common denominator of 1 and cos x is cos x. This means that the numerator will be cos x plus sine x. And because we have one term in the denominator, we can multiply by the reciprocal of the fraction we are dividing by. If we put brackets around sine x plus cos x, we can cancel as follows. This gives the final simplified answer of cos x. Please pause the lesson if you need more time to check my working. Let's see how to use the two identities to help prove the following statement. In cases like this, we talk about the left-hand side and the right-hand side. What we need to do is to show that the left-hand side is equal to the right-hand side. We always begin by working with one of the sides. In this case, I choose the left-hand side. Let's begin by adding the two terms inside the bracket. I hope you agree with this denominator. This means that the numerator will be 1 plus sine theta plus 1 minus sine theta. If you're not sure about this step, it may be necessary for you to do the grade 10 lesson on algebraic fractions. In the numerator, we have like terms which we can collect. This simplifies to 2. If we multiply out the brackets in the denominator, we get the difference of 2 squares. Do you recognize what we have here? We have the square identity in this form, which means we can rewrite the denominator as cos squared theta. How does this help? It means that we can cancel as follows, giving us an answer of 2, which is what we want. This completes our proof because we have shown that the left-hand side is equal to the right-hand side. Please pause the lesson and make sure you agree with my working. Let's prove this one together. Here both sides look almost the same, so it does not really matter which side we start with. Let's begin with the left-hand side. Everything is given in terms of sine and cos, and we cannot apply any of the identities. So it looks as though we can't really do anything here. Let me show you a neat trick. I begin by multiplying by 1 plus cos A over 1 plus cos A. I can do this because multiplying by 1 does not change the value of the left-hand side. But please note, this is not just any one, it has been carefully selected. Next we multiply the numerators, which I will leave in the brackets for now. When I multiply the denominators, I get the following difference of 2 squares. Do you recognize what we have here? The denominator is the square identity written in a different way. In other words, we can rewrite this as sine squared A. We now have one term over one term, which means we can cancel as follows. This leaves us with 1 plus cos A over sine A, which is the right-hand side. Our proof is therefore complete. Please pause the lesson and make sure you agree with my working. In the next example, we need to use our knowledge of reduction formulae as well as identities. Cos 180 degrees minus y reduces to minus cos y. Tan 180 degrees plus y reduces to tan y. And cos 90 degrees plus y reduces to minus sine y. We have now reduced all the angles to y. Next we use the quotient identity to rewrite tan y as sine y over cos y. We can therefore cancel on top as follows. This then simplifies to minus sine y over minus sine y, which gives a final answer of 1. Please pause the lesson and make sure you agree. Let's do one more example together. Here we are again asked to show or prove that the left-hand side is equal to the right-hand side. And it looks as though we will need to use both the reduction formulae and the identities. Let's begin with the left-hand side. Sine minus A reduces to minus sine A. Sine A plus 90 degrees reduces to cos A. Tan 360 degrees minus A reduces to minus tan A. Let's leave cos B as it is for now. And sine 90 degrees minus B reduces to cos B. Next we use the quotient identity to rewrite tan A as sine A over cos A. And cos B times cos B is equal to cos squared B. Cos A cancels out cos A, and sine A cancels out sine A. This simplifies to 1 minus cos squared B, which is just the square identity written in a different way. In other words, we can write sine squared B in the next line of working. This is exactly what we are looking for, and our proof is complete. This completes the lesson for today. Good luck with your test.